an equation of the form y equals a times b to the x power plus c is an exponential function. And I want to show you in this video how to graph exponential functions, how the value of a, b, and c alters the graph of exponential functions, and also how to go backwards from a picture of a graph of an exponential function to calculating the values of a, b, and c. So I'm going to first look at ones that don't have an a or a c, but just things of the form y equals b to the x power. The graph of this depends on whether b is greater than 1 or whether b is between 0 and 1. So I'll start with things of b is greater than 1. The easiest example is y equals 2 to the x power. If you make a little chart where I can pick independently any x values here. And if I calculate out 2 to the 2, 2 to the 1, 2 to the 0, 2 to the negative 1, and 2 to the negative 2, and then if I were to graph these points, 0, 1, 1, 2, 2, 4, negative 1, half, and negative 2. Connecting those dots doesn't make a line, it makes this thing. It looks almost like part of a parabola. But it's part of a curve that actually continues like this. And as x becomes more and more negative, the y value gets closer and closer to 0, but it never makes it to 0, so we get this, which I'll draw in as a blue asymptote. So things to notice. One is that this has a y-intercept of 0, 1. And another thing is that it has an asymptote, horizontal asymptote at y equals 0, or the x-axis. And as long as b is bigger than 1, you do get this shape. If b was like 3, for instance, it might be like go up like this more, but still go close to 0 on the left. If b is like 1.5, maybe it goes like that. But all those have the same kind of shape. They kind of it's like they start off close to the axis and then go up like this. Now there is no vertical asymptote. It looks like there is, but it is very steep, but there's not actually a vertical asymptote, and you shouldn't indicate that there is one because there is not. Now, when b is between 0 and 1, for instance, if b equals 1/2, this becomes y equals 1/2 to the x power. 1/2 to the x power, if I made a chart for that, 2, 1, 0, minus 1, minus 2, we get 1/4, 1/2, 1, 2, 4. So that would look like this, still 0, 1, but now it's got 1, 1/2, and 2, 1/4, and negative 1, 2, and negative 2, 4. That ends up being a mirror image of the last one. Still has a horizontal asymptote on the x-axis. And one reason to show that this should be a mirror image of the other one is if we wrote 1/2 as 2 to the negative 1 power, it would become 2 to the negative x, which is like 2 to the x, except the minus in front of here reflects it over the y-axis. If there is something like 2 to the x, then there's like a minus 1 here. What that does is it shifts everything down by 1, and by everything I mean that includes the horizontal asymptote. So if there's a number here, which I've been calling c, that changes the horizontal asymptote. It also changes the y-intercept, because instead of being at 0, 1 now, it's at 0, 0, and we'd end up with something like that. So this affects the horizontal asymptote. Now the only variable I haven't mentioned yet is the a value. For now I'm not going to have a c, I'll just have an a and a b. So for instance, y equals 2 times 3 to the x power. First thing to mention, that's not the same thing as 6 to the x power. And if I made a chart, x, y, 2, 1, 0. When I put 2 in for x, I get 3 squared, which is 9 times 2, which is 18. And 1 in for x becomes 3 to the 1, is 3 times 2 is 6. And when I put 0 in, I get 2 times 3 to the 0, which is 2 times 1, which is 2. So the x-intercept, at least when there's no c value, will be the value of a. When I plot those 3 points, I get 0, 2 now, and 1, 6. This is not able to draw it perfectly to scale, but the thing I want you to know is that the asymptote would still be, the asymptote is still at 0. It takes longer to approach 0, it gets there slower, but still has that asymptote. So this c is still the asymptote regardless of whether there is a number in front of there for a. And here's one that has a, b, and c. So the c tells me where the horizontal asymptote is. The fact that b is positive means we can expect some kind of shape like that. The y-intercept is pretty useful. If you plug 0 in, you end up with 2 times 3 to the 0 is 1, so 2 plus 1, which is 3. And in general, it's going to be a plus c. So for this one, that, and I can get more values if I want, but even just from this, and the fact that when b is greater than 0, this happens, I can get a pretty good picture. On the other hand, if this was a 1/3 instead, then I would have a picture like that. So just from knowing whether b is greater than 0, or in fact, whether b is greater than 1, or whether it's between 1 and 0, and the value of c and a can get me a pretty decent picture. Now I'm going to go over 4 examples of how to go backwards if we know 2 points on the exponential curve and we know the horizontal asymptote, like in this case. So looking at this graph here, we can definitely say if it's going to be a times b to the x plus c, we can see right away that c is 0 because that's the horizontal asymptote. So now it's just a matter of getting a and b. Now, if one of the 2 points happens to be the y-intercept, that's going to be really useful, because if I take this equation, now that I know that c is 0, and I plug in 2 for y and 0 for x, we end up with 2 equals a times 1, or a is equal to 2. So now I've got almost my whole answer, I just don't have b. Well, the way I get b is I take the equation I have so far, which is y equals 2 times b to the x plus 0, or just times, I don't need the plus 0 anymore, and if I plug 218 in for x and y, I get 18 equals 2 times b squared. That 2 came from here. And now I can solve for b, divide both sides by 2, get 9 equals b squared, and say b, we'll just take the positive value, b is generally positive. So we're done, is 2 times 3 to the x power. And that's when it's easiest when the x-intercept, when the y-intercept is known. This one's a little bit harder. It is going to be in the form y equals a times b to the x plus c. Easiest thing to see is the value of c, which is 4. And now, since I know it's like this, a times b to the x plus 4, and I have a y-intercept, and that's really good because if I plug 0 in for x and 7 in for y, I get 7 equals a times b to the 0, which is just 1 plus 4, which is just a plus 4, so a is equal to 3. And in general, the 7 is going to be a plus c. So once we knew c was 4, we knew a had to be 3. And now I've got a and c figured out. To figure out b, all you have to do is take the other point, the 216, plug in 16 for y, plug in 2 for x, subtract 4 from both sides, divide both sides by 3, and b is equal to positive 2. So the answer is y is equal to 3 times 2 squared plus 4. Sorry, y equals 2 to the x plus 4. This is A, B, and C. So those are the two cases where the y-intercept is known. Now let's look at two cases where we don't know the y-intercept. Those are a little bit harder. Okay, here's one where the asymptote is at y equals 0, and the two known points are 4, 7, and 10, 12. We don't know the y-intercept. This one's a little bit harder. We do know that c is 0, so it's going to be a times b to the x, plus 0, but I don't need that. But now how do I get a and b? Well, here's a sneaky trick for that. I take the one that's got the bigger x value, and I substitute 12 and 10 in for x and y in this equation. So it becomes 12 equals a times b to the 10th. Then I take the 7 and 4 and do the same thing. So I get 7 equals a times b to the 4th. This is a system of equations which we can solve by dividing the two things. We get 12 over 7 equals b to the 6th power. You divide by subtracting the exponents. And b would be the 6th root of 12 over 7. On a calculator, you could do 12 over 7 to the 1/6 power, or various ways. You get 1.094. It's good to round b to the nearest thousandth. Now that I've got b worked out, I can take either of these points. I'll use the 4, 7, and basically this equation here, but I'm going to substitute b in, so I get 7 equals a times 1.094 to the 4th power, raise to the 4th power, and divide by that, and I end up with a is approximately 4.9. I like to round a to the nearest tenth. So we get an equation of 4.9 times 1.094 to the x power. So that is an example of, we don't know the y-intercept, but c was 0. The final example is one where we will have two random points, not the y-intercept, and the horizontal asymptote will be something other than the x-axis. So in this one, the 2 points are 4, 8, and 10, 18, and the asymptote is here at y equals 1. This isn't really drawn to scale except the asymptote. So the way we do this one, just like before, our equation is going to be y equals a times b to the x plus 1. We know what c is already. So if I take the one with the bigger x coordinate and say 18 equals a times b to the 10th power plus 1, then take the other point and say 8 equals a times b to the 4th plus 1. And here's where you have to be extra careful. Don't divide yet. First subtract 1 from both sides. 17 equals 8 times b to the 10th. And 7 is 8 times b to the 4th. Now you can divide both sides and get 17 over 7 equals b to the 6th, or b is equal to the 6th root of 17 over 7, which is about 1.159. And I'll take this equation here and do a is equal to 7 over that 1.159 to the 4th power. And we get about 3.9. So this one would be y is equal to 3.9 times 1.159 to the x power. Don't forget, plus 1. Okay, so those are all the things that can happen. This is a pretty useful skill to have, because there'll be times in the real world, they'll tell us that the population of some country, is 400 million. In 1990, what is called years since 1990. Whoops, over here. Years since 1990. And then they tell us that in the year 2020, so 30 years later, the population's gone up to 500 million. And based on that, we can get the equation of the exponential and then use it to predict the future. Another situation, one where b would be less than 0, is one where you take food out of a hot oven, and after a certain amount of time the food's cooled off, and then more, it cools off more, it's getting closer to room temperature. That also follows exponential. So if I know room temperature and I know these 2 points, I can calculate out an equation that would relate temperature to time, or time to temperature. Okay, so that's how you do it. I hope you like that video.